Before I start, this is a Slido, a QR code. You know how it works. I think I understood how it works. So if you have any questions, you can scan this code, write it, and just send a question to me. I'll be happy to answer if I get any questions at all, because I am going to talk about something that is not so, I mean, I started with this Java song, but then it's not so Java related. I just want to explain how did we get there. And me, I'm as a astrophysicist turned developer in machine learning and AI, and also bass player of Nanowar Of Steel. If any one of you knows the band, is the author, is the band that authored the song that I just showed. And so I want to start a little bit talking about how I got into the world of developing and how this affected the all the musical production and other things that we did with the band. So I hope you find it interesting, though it's not so strictly Java related. So let me start with me. I started with all of us, actually, because I want to talk about the universe. So I started as an astrophysicist and a computational astrophysicist, which means that I was running simulations to basically to simulate the history of the universe. And so it turns out if you do this, you want to basically see how, according to mathematical models, you want to simulate how the universe starts. So now what you see here is a picture that on the x-axis shows the various slices at different times. So this is on the x-axis is the time evolution. And you see on the 2 dimensions, then you see slices that look that show pictures of how the universe looks like. So what you want to do is start from an initial state of particles. You want to put them into a computer and use the computer to run simulations of these particles, how they interact, and how they eventually end up creating galaxies, stars, and everything that we see. Because the universe is a very complex system, as you might imagine. You don't need a PhD in astrophysics to deduce that, because you start from structures like the Earth, which is a small planet, which is part of a solar system, which is part of a solar interstellar neighborhood, which means it's a bunch of planets and stars that live in our neighborhood, so a few light years away from us. But then we leave all this, our solar interstellar neighborhood is just a tiny dot in the Milky Way galaxy, which is, again, itself is part of the local galactic group, which is a number. There's a number of a few tens of galaxies that live around us, and all of these galaxies are part of the Virgo supercluster, which is part of the local supercluster, which is part of the observable universe. And so when you run cosmological simulations, you want to simulate basically how all these things. How come you find all these things? How you have all these different scales going on at the same time? And to do that, it turns out you really do need to do a lot of computing. And so I started this actually in Heidelberg, where I was also working as a Java developer as a side job. That's how I got started into Java. But most of the simulations are actually run in C, C++, with MPI and OpenMP, so you have different protocols to and different modules to frameworks to address the how do you distribute the memory, how do you distribute these computations across different nodes. So when you have HPC clusters, the clusters with a lot of CPUs, then you want to spread all these billions and billions of particles you have across these different nodes, and so you can actually simulate this. Because as you see, this is a box like what you see in the upper corner at my right. It's the universe at the start, so you start with a bunch of gas, you have gas particles, and then you want to simulate. So at every step, this is basically a few million years after the Big Bang, you have all this gas everywhere, and then this gas condenses into tighter structures, and it creates these filaments, and within these filaments then you have the formations of stars, galaxies, and so on and so forth. So you end up with the image there on the bottom at my left, down there, and that's the final thing that you want to simulate. This is the universe today, and you want to have a picture of all these things together, and that's the thing. So you need to do a lot of data analysis, of course, because you have a lot of data coming on from deep simulations, you have billions of particles and terabytes of data you need to analyze. And so that's got me into machine learning at some point, and this is just to show a paper how we're using these simulations basically as a sort of mock-up, as a sort of fake data that we could train the systems on and then apply this systems, a machine learning system, to observation, to extract from observation variables that are not observable. So basically what do I mean is if you have a simulation, of course, for every star that you simulate, it's in your computer, you know all the variables, you know all the values, you know what's the mass, you know the luminosity, you know how bright it is, you know everything. So when you observe the star in the universe, you cannot really measure it directly. And so what you want to use machine learning for is basically to find the features that you can actually observe, to infer the features that you cannot observe, if you're familiar with the machine learning language. And so this is regarding my academic career. At some point I realized that you could point the telescopes in the wrong direction, so not to look at the sky but to look at the Earth. And then it turns out that if you do Earth observations, you can find a job much easier. And so I moved to industry, working in Earth observations and machine learning and computer vision, and doing this basically. So you have several missions from ESA and NASA that release free data that is taken on they are taking multispectral images of the surface of the Earth, so they're taking pictures that do not only capture the RGB contents of the surface of the Earth, so not just the visible light basically, but also the non-visible, invisible light. You can have images in the infrared and ultraviolet and so on and so forth, so you have more information on the surface of the Earth, and these satellites are basically free. What does it mean? You can get the data, they are open access, and they take pictures on a regular scale. So for example, if you want to monitor some remote place, you don't need to go there with physically. If you want to monitor the Amazon, or you want to monitor even some forest on some mountain, you don't need to go there on a weekly basis to see, for example, what's the status of health of the vegetation. So this is just to show you what multispectral imaging data is. You are taking pictures at different wavelengths. So you have the electromagnetic spectrum on top there, and this is taken from the Sentinel-2 mission from ESA, and it's taking basically 13 bands, so which means that 13 different frequencies, which means you don't only you not only have RGB, but you also have many other informations taken from the light that is reflected by the surface of the Earth. So again, as I was mentioning before, you don't need to. You do not only capture what you can see. You can capture many more information, because there's a lot of materials on the surface of the Earth that reflect light, reflect electromagnetic waves at frequencies that we do not see. So we can get. We do not see with the eye, so we can get much more information. Now, one problem of this is, of course, that when you're taking these kind of pictures, if you have clouds and atmospheric perturbations, you don't really see much. You need to correct for that, and there's algorithm and there's all a different business, but it's sort of a hassle. So, but again, this is just to introduce, give an overview of the field. And this is, for example, a picture of part of Venice. You can see how it looks like on the RGB, and on the black images, the black and white is infrared, near infrared image. So it's taken when you take this band and you convert it into black and white, then you see these kind of things. Now, the interesting part is when you combine all this information together, you can get these so-called multispectral indices. There are values that you basically just take all these things are tensors, are vectors, matrices. Every layer is basically a matrix, and so every matrix corresponds to a layer. So it corresponds, for example, it's like in usual RGB images, right? You have these RGB layers, and you have more in this case, so you can combine these layers, and you can get information about the vegetation, for example, as I was mentioning. So When you combine the indices, so-called NDVI index, it's normalized this different vegetation index, which is a quantity that is within these values, is telling us, for example, in the black area, is telling us where the water is, and the different shades of green tell us if there is a field or if there is a tree. And so depending on how this, of course, how this value changes with time, because satellites take pictures of the Earth on a regular basis. So you can see the evolutions. You can see if there is deforestation. You can see if there is vegetation increasing, decreasing, if the health of the vegetation is good, and so on and so forth. You can see also the expansions on the city, because some values of this index are related to the presence of structures of asphalt and other buildings. So another cool implication of all this is that you can, once you know, for example, the level of health of the vegetation, you can build fire risk indices. So you know if the vegetation is dry, if there is no humidity on the ground, for example, and then you combine that with meteorological data, then you can combine those data and build maps. This is a map of Sardinia, for example, with different shades of color, where you see the reddest area are showing where the actual danger is. So there can be a danger that can be in risk of wildfire. So you don't need, again, you don't need to monitor everything with sensors and send everyone everywhere to see if there is some smoke, if there is anything weird going on. You can actually take regular picture on a regular basis from the space, and then this database of pictures that you get will tell you basically where the danger, where you have the highest problems, where you are likely to have the wildfires. Of course, we cannot account for human-made fires. And so this is everything, all the world regarding the Earth and astronomy, and how I got into programming. So I'm working on these issues. But the other part of the talk, and the other final thing, is related to the song that I was showing you before. And it's related to Nanowar Of Steel. And I'm going to talk about Uranus and Hello World.java. And so Uranus is a song, of course, and Hello World.java again as well. And I have another song that I will show you at the end of the talk. It's going to be the very first time. It's a demo, so I will show that as well, although I'm not mentioning it here. So this is just to show you, 2 years ago we celebrated 20 years of existence with this show in Milan, in Alcatraz, and it was a cool show. More than 3,000 people came, and well, anyway, we are on tour all the time, so sometimes you can catch us. I don't know if some of you already saw us live. Probably we played in Germany pretty often. So, and there are some pictures from one of the videos, one of the most famous probably videos that we released. It's called Uranus. It's about the planet, but probably you can see there might be a stupid joke with words over there, but these are some pictures taken at the observatory. We filmed the video in an actual astronomical observatory. Used my astrophysical connection to get there, and it was cool. It was a very nice location, except the guys at the observatory didn't really understand the joke. And they understood it when it was too late. And we got into some kind of fight, so we had to remove the observatory from the credits because they didn't want to be mentioned there. But let me just show you the video so you can judge for yourself.
I like it big, I like it cold, I like it blue, I like it bold, I like it with the 2% of methane. I want it icy, I want it large, want it spicy with electric charge, fluid outside and rocket side.
Well, this was just a piece of the video. I hope you didn't find it too extreme in language, and I didn't censor it so much. But so this is the first kind of scientific song we released. Until last December, we released Hello World. It's I'm pretty proud of, I think it's the first song that also has a public repository that you can contribute to if you want. It's on GitHub. Of course, I don't know if any one of you maybe submitted some requests. I think we lost the track at some point. We just didn't accept pull requests anymore. But and so what I showed you before, it's probably the first source code video. I think. Let me stress, it's not generated with AI. We still write songs in the old-fashioned way. We are old-fashioned. Will be probably replaced very soon. But as long as we can do that, we enjoy writing songs. And so it's the first song that we actually took the actual code is just the lyrics of the song. So we are pretty proud of that. And most of that is thanks to our guitar player. He's an actual Java developer and CTO. In his he works in he also has a double position as a CTO and a guitar player of Nanowar Of Steel. We don't know what's our main job, but anyway, so we both have to fit into this IT world and music as well. But you might have noticed that the song that I showed you at the beginning ended with a very serious bug. There was a null pointer exception, and we had to work on that. And JetBrains stepped in to help. Of course, we needed to solve a null pointer exception problem of that kind. It's something that we really need some serious help to get it to solve it. So we have basically just replaced that line using IntelliJ IDEA with AI powered to set the variable metal to true instead of false. So that's probably the dumbest bug in human history, but we solved it thanks to IntelliJ IDEA. So, and with JetBrains, we released a patch for the song. So now we have two versions. You have the first buggy version of the song, and there's a song with a patch. And I'm showing you the patch now. So this is how the song ended. Very sad. And now, fix with AI. Very important. We couldn't do it ourselves.
System out of pre-intelligent. Hello world. Semicolon. System out of pre-intelligent. Hello world. Semicolon. System out of pre-intelligent. Hello world. Semicolon.
So this is how the song should end properly when you fix it with IntelliJ. It was really, I really must thank JetBrains for solving this unsolvable issue. Do you think you guys solved it? Raise your hands if you knew how to solve it without an IDE so powerful. No one can solve it, you see, it's a very bad bug. And so this is just to wrap up my talk and showing you, I got it yesterday, it's we have a new song coming out in dev metal. It's probably going to be the new trend in metal, I'm not sure, but I hope so. And so the next song in dev metal is about Kotlin. And we just got the first preview of the video. And I'm gonna show it to you, I hope. Who uses Kotlin here? Is it just pure Java or is any Kotlin developer as well? Okay. Enjoy.
Imagine a Java language with no unnecessary verbosity, combining strong type checking with all research exists, and it's causing no formal points or exceptions with variable data types. Definable access and Elvis operator. Read all them multiple variables with the almighty bar and ball. Mutability of collection. All for fun, fun for all.
That's it. It's just a preview. It's gonna. We're actually showing it. So next week, no, in 2 weeks, more or less, we're going to J Nation in Portugal. I don't know if any one of you is going there. Yeah, then okay. You've seen this. Don't tell it to anyone. It's a secret, but we're gonna play there at the conference. They invited us, so we're gonna play and we're gonna show this. New song as well, and it's going to be, I think, the first talk where you have a band talking, and the slides are actually the song lyrics. I don't know. We try to do something really crazy. So, but this was all I wanted to tell you today. I hope you enjoyed the talk, and thanks a lot.